Hi everyone, my name is Yuehan Chen, and I'm going to present to you my data science project, Finding Donors for a Charity, which is a Kaggle competition. Let's first look at the dataset overview. This Kaggle competition provided the data extracted by Barry Becker from the 1994 Consensus database. It contains individual data such as education levels, work class, marital status, occupation, and etc. The problem statement of this dataset is that a charity in this competition wants to utilize this dataset to find potential donors whose income exceeds $50,000 a year to reach out to ask for a donation. There are 8 steps in this process. I first assess the data, and then I preprocess the data. And then I calculate the performance of a naive predictor. In the fourth step, I select the 3 appropriate model candidates, and then I create a training and predicting pipeline to see each of the 3 models' performance. And then I evaluate the 3 initial models and pick the best model. In the 7th step, I tune the model, and then I present the competition result. Now first, look at the step 1, assessing. This dataset has 14 columns, 55,000 rows, and 0 missing value. And there are 5 numeric features, including age, education number, capital gain, capital loss, and hours per week, as they are in different scales, so later I will conduct normalization on them. And there are 8 categorical features, including work class, education level, marital status, occupation, relationship, race, sex, and native country. And I will one-hot encode them. And the last column is the target variable. It contains the string value of smaller than or equal to 50K or bigger than 50K. And later I will map these string values to 1 and 0. Now let's look at the distribution among age, capital gain, and capital loss. As you can see, they are skewed to the right, and age is just slightly skewed to the right, but capital gain and capital loss are very extreme. So later, I will transform them by using logarithmic transformation. In the second step, I preprocess the data. I first transform age, capital loss, and capital gain, and then I normalize all the numeric features. Then I mapped the target variable into 1 and 0. Lastly, I one-hot encode all the categorical features. In the third step, I calculate a naive predictor's performance. And the purpose of creating a naive predictor is to show what a base model without any intelligence will look like. So when you present your report to managers, they can compare it with other machine learning models to see if those smart models are really adding values. And throughout this project, I will use accuracy and AUC to see the performance of each model, as the Kaggle competition will rank the submissions by its AUC. Here, I set a naive predictor that always predicts 1, i.e., the individual makes more than 50K. The model will have no true negatives or false negatives, as I'm not making any negative predictions. And as we have 11,000 true positives and 44,000 all positives, and we will get the accuracy rate of 0.24. Now for AUC, let's look at the next slide to see why it's 0.5. AUC is calculating by projecting all the prediction results, i.e. the probabilities of each point belong to positive and negative, into a one-dimensional line. Then we calculate the true positive rate and false positive rate of several points in that line. And then we plot all those points into a 2D chart where you can calculate the area under curve. Now here, the naive predictor predicts all the points to be positives. So if we calculate the true positive rate or the false positive rate, we'll get 1, 1, because for positive rate, there is no false negative. So since the numerator is true positive and the denominator is also true positive, we will get 1. And then for the false positive rate, since we don't have true negative, so false positive divided by false positives, we will also get 1. So all the points on the left of all these points here will get 1, 1 because of the same logic here. And then the point on the right of these points is 0, 0 because there is no true positives and also you don't have any false positive. And as we plot all these 1, 1 and 0 into this 2D chart, we can see that the area is actually a triangle area and the area is 0.5. In step 4, I list 3 supervised learning models including random forest, gradient boosting, and XGBoost that I think are appropriate in this dataset. Now, in step 5, I create a training and predicting pipeline. And the purpose of the pipeline is that it allows you to quickly and effectively train models using various sizes of training data and perform predictions on the testing data so that we can see whether it is overfitting or underfitting. This pipeline will do 5 things: training, predicting, documenting the training, predicting time, and calculating accuracy and AUC. Now let's look at the function of this pipeline. We need to give 6 inputs to this pipeline. The first one is the model that you want to train and predict. And the second one is called sample size, as we will see the learning curve of each model performing on different sample sizes. So here we will give it the sample size. And then we will give it X-train, Y-train, X-test, Y-test. The first thing we do in this function is we created a dictionary called results, and it will document all the results that we want to see. And then we save the start time, and then we train the model, and then we save the end time so that we can calculate the training time. We do the same thing when we predict the data, and then we can save the predicting time here. Now, after we predicted the data, we can calculate the accuracy score on training set and testing set. And we can also calculate the AUC on training set and testing set. And this is my pipeline. Now, in 6 steps, I evaluate all these 3 initial models, and then I will pick the best model. This is the results that I got after I ran a for loop to give the pipeline each model with 1%, 10%, and 100% training set. And I concluded that the best model is XGBoost. There are 3 reasons. The first one is for this graph. We can see that random forest is overfitted a little bit as it has high training score here and it has relatively low testing score. In contrast, XGBoost performs the best as it gets the highest testing score. And also the training score it got is similar to its testing score. So that means it's neither overfitting nor underfitting. The second reason is that although XGBoost spent the highest amount of time on training, it only takes 12 seconds, so it's acceptable in this dataset. Lastly, remember that 0.24 accuracy and 0.5 AUC we got from the naive predictor? XGBoost performs way better than that, with an accuracy of 0.85 and an AUC of 0.8. So we'll be using XGBoost to predict the testing set on this Kaggle competition. Here is the simple explanation on how XGBoost works. Imagine asking a bunch of high school students to solve a set of college-level math questions. Each high school student has some level of math knowledge, but none of them is incredibly talented or terrible at math. The students take turns to solve the problems, and the teacher will give them a score after they finish the questions. Besides, the teacher will tell the next student what questions the previous students has done wrong so that they will be more mindful of those questions. It will repeat the process until every student has answered the questions. In the end, the teachers trust more on the answers given by the students who got high scores and trust less on the answer given by the students who got low scores. And she answers the questions herself. And this is a basic explanation of how boosting algorithm is trained. In 7 steps, I tune the XGBoost model. Here is the parameters that I want to test, and each parameter has 2 possible values, and the total possible sets of parameters are 2 to the power of 5, because there are 5 parameters, which equals 32. So if I used the grid search, it will run 32 times to find the best one. And since it will be using either 300 or 400 estimators to test, it can take super long to run it 32 times. Therefore, I use the randomized search to find the best set of hyperparameters, which will randomly select the sets of hyperparameters to test. So it isn't guaranteed to find the best one, but it runs faster. And here is the result. We can see that both accuracy and AUC increased a little bit. Lastly, I used the optimized XGBoost to predict the testing data from the Kaggle competition. And here is the result. Out of 212 things, I was ranked 30th place. Thank you so much for listening to this presentation, and I hope you have a good day.